If you like this video, be sure to subscribe and hit the bell icon. Share it with a friend and I'll be doing more videos like this just for you. Did you ever call someone or send text messages using your smartphone? Have you ever tried heating food using a microwave oven? When was the last time you tuned in to your favorite radio station? Did you know that these mentioned activities have something in common? It's electromagnetic waves. Everyday life is pervaded by artificially made electromagnetic radiations, like food is heated in microwave ovens, airplanes are guided by radar waves, television sets receive electromagnetic waves transmitted by broadcasting stations, and infrared waves from heater provide warmth. In your grade 7, you were able to learn the concepts of waves and its characteristics. Let us review if you can still remember these concepts. Make sure you have a piece of paper and a pen with you where you are going to write the correct answer. Remember, questions will be flashed for 10 seconds. You can pause the video if you needed more time. Are you ready? It's a 6-letter word which means blank travel in waves. What is the word? The correct answer is energy. Energy travels in waves. Five-letter word. Transverse waves moves up and down in patterns that have high points called blank. What is the word? The answer is crest. Transverse waves move up and down in patterns that have high points called crest. 6-letter word. The low points of a transverse waves are called blank. The correct answer is straw. The lowest points of a transverse waves are called straw. 10-letter word. The distance between any two troughs or peaks is called blank. Guess the word. The answer is wavelength. The distance between any two troughs or peak is called wavelength. 9-letter word. The height of a peak or trough is called blank. What is that word? The correct answer is amplitude. The height of a peak or trough is called amplitude. 9-letter word. The number of complete waves that pass by in 1 second. What is the word? The number of complete waves that pass by in 1 second is called frequency. 5-letter word which means frequency is measured in blank, which is written in Hz. What is that word? Frequency is measured in hertz, which is also written as Hc. So the correct answer is hertz. 12-letter word. Waves move by pushing forward and pulling backward. Guess the word. Longitudinal waves are waves that move by pushing forward and pulling backward. So the correct answer is longitudinal. 5-letter word. Blank is an example of longitudinal waves. Guess the word. The answer is sound. Sound is an example of longitudinal waves. It's a 10-letter word. Its waves on the surface of water are examples of blank waves. What is that word? The correct answer is transverse. Waves on the surface of water are examples of transverse waves. Identify the type of wave shown in the illustration. The correct answer is transverse waves. Identify the type of wave shown in the illustration. The correct answer is longitudinal waves. I hope you got the correct answers in our activity today. Stay focused and have fun learning! Science Quarter 2 Module 1 Electromagnetic Wave Theory. Our learning objectives for today is we're going to 1. Trace the development of electromagnetic theory. 2. Describe how electromagnetic or EM wave is produced and propagated. 3. Solve problems involving electromagnetic waves. Today we're going to discuss the brief history of electromagnetic theory. In physics, electricity and magnetism often go together. Let us meet the original players in the electromagnetism who laid the groundwork for the understanding of the concept of electromagnetic theory. Here are the proponents on the formulation of the EM wave theory. In 1820, Danish physicist and chemist Hans Christian Ørsted discovered what would become known as the Ørsted law, that an electric current affects a compass needle and creates magnetic fields. He was the first scientist to find the connection between electricity and magnetism. During this time, he made an important discovery that electric current creates a magnetic field. Prior to that, scientists thought that electricity and magnetism were unrelated. But like many other important discoveries in science, Ørsted's discovery was just a lucky accident. André-Marie Ampère, influenced by Ørsted's discovery, performed a series of experiments designed to elucidate the exact nature of the relationship between electric current flow and magnetism, as well as the relationship governing the behavior of electric current in various types of conductors. It was Andre Marie Ampere who demonstrated the magnetic effect based on the direction of current. He made the revolutionary discovery that a wire carrying electric current can attract or repel another wire next to it that also carrying electric current. The attraction is magnetic, but no magnets are necessary for the effect to be seen. He went on to formulate Ampere's law of electromagnetism and produced the best definition of electric current during his time. These experiments led Ampere to formulate his famous law of electromagnetism called after him, Ampere's law, that describes mathematically the magnetic force between two electric currents. Ampere's law states that when the current is flowing through a circuit, it produces a magnetic field of a strength directly proportional to the amount of current flowing through the circuit. In 1821, Michael Faraday made his first discovery of electromagnetism. He took the work of Ørsted and Ampere on the magnetic properties of electrical current as a starting point, and in 1831, he achieved an electrical current from a changing magnetic field, a phenomenon known as electromagnetic induction. Faraday's law of induction describes how an electric current produces a magnetic field, and conversely, how a changing magnetic field generates an electric current in a conductor. He found that when an electric current passed through a coil, another very short current was generated in a nearby coil. This discovery marked a decisive milestone in the progress not only of science, but also of society, and is used today to generate electricity on a large-scale power station. Another important individual who made an important design of improvements by insulating the wire instead of the iron core while working with electromagnets in 1829 was Joseph Henry. He was able to wrap a large number of turns of wire around the core and thus greatly increase the power of the magnet. He had made an electromagnet that could support 2,063 pounds, a world record at that time. He also searched for electromagnetic induction, and in 1831, he started to build a large electromagnet for that purpose. He was the first to notice the principle of self-induction. James Clerk Maxwell. James Clerk Maxwell, 1876, is an English scientist who developed a scientific theory to better explain electromagnetic waves. When Maxwell used his field theory to assume that light was an electromagnetic wave and then correctly deduce the finite velocity of light, it was a powerful logical argument for the existence of the electromagnetic force field. He noticed that electric field and magnetic fields can couple together to form electromagnetic waves. Maxwell discovered that a changing magnetic field would induce a changing electric field and vice versa. Based on Maxwell's findings, he added two basic principles of electromagnetism. 1. A changing electric field in space produces a magnetic field. 2. A changing magnetic field in space produces electric field. Maxwell proposed that the alteration of electric and magnetic fields generating and propelling each other in space can be thought of as a form of moving energy. Maxwell further thought of this form of energy as a wave which he called electromagnetic wave. Using mathematical computation based on his theoretical assumption and the numerical result of Faraday's experiment, Maxwell concluded that the speed of electromagnetic wave must be 3 times 10 raised to 8 meters per second. Maxwell's equations are used today as the basis of electromagnetic theory. Maxwell predicts that the connection of magnetism and electricity leading directly to the prediction of electromagnetic waves. Heinrich Hertz. It was only after the death of Maxwell which Heinrich Hertz, German physicist, designed an experimental setup that was electrical in nature and able to generate and detect electromagnetic waves. He showed experimental evidence of electromagnetic waves and their link to light. Hertz proved the existence of radio waves in the late 1880s. He used two rods to serve as a receiver and a spark gap as a receiving antenna, where the waves were picked up and a spark would jump. Hertz showed in his experiment that these signals possess all the properties of electromagnetic waves. Henry Hertz also discovered the Hertzian wave, which is now known as the radio waves. Hertz is also a man whose peers honored by attaching his name to the unit of frequency. A cycle per second is 1 Hertz. These are the scientists behind electromagnetism and lay the groundwork for the understanding of the concept of electromagnetic theory. Faraday, Henry, Maxwell, Ampere, Hertz, and Ørsted. I hope you can still remember the scientists behind each contribution. This time, we're going to have our learning task number 1. I named it Who's Who. What you're going to do is identify the scientists based on their given contribution. Question number 1. Who demonstrated the magnetic effect based on the direction of current? Faraday, Henry, Maxwell, Ampere, Hertz, or Ørsted? Correct answer is Ampere. André-Marie Ampere demonstrated the magnetic effect based on the direction of current. Question number 2. Who formulated the principle behind electromagnetic induction? Faraday, Henry, Maxwell, Ampere, Hertz, or Ørsted? The correct answer is Faraday. Michael Faraday formulated the principle behind electromagnetic induction. Question number 3. Who showed experimental evidence of electromagnetic waves and their link to light? Faraday, Henry, Maxwell, Ampere, Hertz, or Ørsted? The correct answer is Heinrich Hertz. He is the one who showed experimental evidence of electromagnetic waves and their link to light. Question number 4. Who contributed to developing equations that shows the relationship of electricity and magnetism? Faraday, Henry, Maxwell, Ampere, Hertz, or Ørsted? Correct answer is James Clerk Maxwell. He is the one who contributed to developing equations that shows the relationship of electricity and magnetism. Question number 5. Who showed how a current-carrying wire behaves like a magnet? Faraday, Henry, Maxwell, Ampere, Hertz, or Ørsted? Correct answer is Hans Christian Ørsted. He is the one who showed how a current carrying wires behaves like a magnet. Do you have any questions so far? If there's none, we can proceed with our next discussion. At this point, we are going to discuss the basic concept of waves. So, what are the parts of a wave? Wave is the repeating and periodic disturbance that travels through a medium from one location to another location. Wave crest is the highest part of a wave. Wave trough is the lowest part of a wave. Wave height, the vertical distance between the wave trough and the wave crest. Wavelength is the distance between two consecutive wave crests or between two consecutive wave troughs. Wave frequency is the number of waves passing a fixed point in a specific period of time. Wave period is the time it takes for two consecutive crests or one wavelength to pass a specific point. The wave period is often referred in seconds. Example, one wave every 6 seconds. We are surrounded with thousands of waves. They collide with our body and some pass through us. Mostly are invisible, but we can perceive some. The warmth of the sun and the light that we see are just few of them. These waves share familiar characteristics, yet they are unique in some ways. These waves are called electromagnetic or EM waves. What is an electromagnetic wave? Electromagnetic waves or EM waves are waves that are created as a result of vibrations between an electric field and a magnetic field. In other words, EM waves are composed of oscillating magnetic and electric fields. So what's the difference between electromagnetic wave and mechanical waves? A mechanical wave is a wave that is not capable of transmitting its energy through a vacuum. Mechanical waves require a medium in order to transport their energy from one location to another. For a mechanical wave to travel, it must vibrate the medium as it moves. This makes use of some of the wave's energy. In the end, it makes them transfer all the energy to the medium. A sound wave is an example of a mechanical wave. Sound waves are incapable of traveling through a vacuum. Don't you know that there are two types of mechanical waves? The two types of mechanical waves are longitudinal waves and transverse waves. Transverse waves vibrates the particles of a medium perpendicularly to the direction of a wave travel to produce the features as shown below. Longitudinal waves form when the particles of the medium vibrates back and forth in the same direction of the traveling wave. The wave can be visualized as compression and expansion traveling along the medium. The distance between adjacent compression is the wavelength. EM waves, on the other hand, are disturbances that transfer energy through a field. They can travel through medium, but what makes them strange is that they can also transmit through empty space. Radiation is the term used to describe the transfer of energy in the form of EM wave. Electromagnetic waves differ from mechanical waves in that they do not require a medium to propagate. This means that electromagnetic wave can travel not only through air and solid materials but also through the vacuum of space. As for EM waves, they can travel through empty space or vacuum, so they do not give up their energy. Electromagnetic waves that are produced on the sun subsequently travel to Earth through the vacuum of outer space. Were it not for the ability of electromagnetic waves to travel through a vacuum, there would undoubtedly be no life on Earth. All light waves are examples of electromagnetic waves. This enables EM waves to cross great distances such as that from the sun to the earth, which is almost vacuum without losing much energy. In vacuum, EM waves travel at a constant speed of 300 million meters per second or 3.0 times 10 raised to 8 meters per second. At this rate, the rays of the sun takes 8 minutes to reach the earth. Properties of electromagnetic waves. There are many properties that scientists use to describe waves. They include wavelength, amplitude, frequency, period, speed, and phase. Wavelength is the distance between two identical points on successive waves. In most cases, wavelength is measured according to the distance between two successive wave crests or two successive troughs. A higher frequency causes a short wavelength and greater energy. So, a longer wavelength means a lower frequency, and a shorter wavelength means a higher frequency. Wave amplitude is a measure of the energy of a wave carries. It is determined by measuring the distance from the midpoint of the wave to either a crest or a trough. Frequency, on the other hand, is the number of wavelengths that pass by a certain point in a given time. A wave with high frequency generally has more energy than a wave with lower frequency. Frequency is expressed in Hertz or Hz. 1 Hertz equals 1 cycle per second. Thus, Hertz can be expressed as number of waves per second. The higher the frequency, the closer the waves are together and the greater the energy carried by the waves. The lower the frequency, the farther the waves are and the lesser the energy carried by the waves. Waves period. Wave period is the time it takes to complete one cycle. The standard unit of a wave period is in seconds, and it is inversely proportional to the frequency of a wave, which is the number of cycles of waves that occur in 1 second. In other words, the higher the frequency of a wave, the lower the wave period. Wave speed. Wave speed is the speed at which a wave travels. Wave speed is related to wavelength, frequency, and period by the equation wave speed is equal to frequency times wavelength. The most commonly used wave speed is the speed of visible light, an electromagnetic wave. Wave phase. Wave phase specifies the location or timing of a point within a wave cycle of a repetitive waveform. All electromagnetic waves can travel through a medium, but unlike other types of waves, they can also travel in vacuum. They travel in vacuum at a speed of 3 times 10 raised to 8 meters per second and denoted as c, the speed of light. The wave speed, frequency, and wavelength are related by the following equation. V equals to lambda f, where V equals to wave speed or C's speed of light expressed in meters per second. Lambda equals to wavelength expressed in meters, and F equals to frequency expressed in hertz. Since all the electromagnetic waves have the same speed, and that is equal to the speed of light, as wavelength increases, the frequency of the wave increases. Through the years, the advancement on the knowledge about electromagnetic wave led us to a modern technological world. Now, we are going to solve some sample problems on electromagnetic waves. Let's have question number 1. What is the frequency of a wave with wavelength of 20 meters? With this problem, let's first identify the given, and that is wave speed or V equals to the speed of light is equals to 3 times 10 raised to 8 meters per second, and this is constant value. Lambda is equals to 20 meters, which is also the wavelength. And what is asked or the required is frequency, that is F equals to unknown. For our solution, from the original formula, that is wave speed equals to the speed of light equals to wavelength times frequency, we will derive the formula for F, which is F is equals to the speed of light divided by the wavelength. Substituting the values, we will have F equals to 3 times 10 raised to 8 meters per second, which is the value for the speed of light, and that is constant, divided by the value for the wavelength, that is 20 meters. So if we're going to divide these values, our F will be F equals to 1.5 times 10 raised to 7 Hertz. Now let's have sample problem number 2. Calculate the wavelength of radiation with a frequency of 610 kHz. Note that 1 kHz is equals to 1000 Hz. In the problem, we are going to identify the following. First, the given. We have wave speed or the speed of light, which is constant, that is equals to 3 times 10 raised to 8 meters per second. And frequency is also given, which is equals to 610 kilohertz. Our unknown or required is the wavelength. For our solution, we're going to use the formula lambda or wavelength is equals to c, the speed of light, divided by f, which is frequency. If you notice, our frequency has a unit of kilohertz, but what we need is hertz. So we are going to use the conversion factor 1 kilohertz equals to 1000 hertz. We are going to multiply 610 kilohertz by 1000 hertz and divided by 1 kilohertz. We will cancel the unit kilohertz and kilohertz, and this will give us 610,000 hertz. This time we're going to substitute the value of C, which is 3 times 10 raised to 8 meter per second, and divided by 610,000 hertz, or 6.1 times 10 raised to 5 hertz. And once we divide these values, we will get the value of wavelength, and that is 490 meters. Are there any questions? I hope you understood our discussion on how to solve or calculate the value of wavelength and frequency. On the next slides are the questions for learning task number 2. Do this task and write your answer in a separate sheet of paper. Our learning task number 2 is you're going to solve the following problems and make sure you show your solution in your answer sheet. Question number 1. What is the wavelength of an electromagnetic wave that has a frequency of 4.95 times 10 raised to 14 hertz? Question number 2. Calculate the frequency of an electromagnetic wave with a wavelength of 4.80 times 10 raised to 17 hertz. For this activity, you were given 2 minutes to answer, or if you need more time, you can pause the video. Let's check for understanding whether you got the correct answer or not. For question number 1, what is the wavelength of an electromagnetic wave that has a frequency of 4.95 times 10 raised to 14 hertz? Based from our given, we have frequency equals to 4.95 times 10 raised to 14 hertz, and our constant value for wave speed or the speed of light is 3 times 10 raised to 8 meter per second. Our required is wavelength. We need to look for the wavelength. So for the solution, we have wavelength is equals to the speed of light divided by frequency. We have to substitute the value of C, that is 3 times 10 raised to 8 meter per second, divided by 4.95 times 10 raised to 14 hertz, which is our value for F. And once we divide these values, our wavelength will be 6.06 times 10 raised to negative 7 meters. For question number 2, calculate the frequency of an electromagnetic wave with a wavelength of 4.80 times 10 raised to 17 Hertz. In the problem, our given are wavelength is equals to 4.80 times 10 raised to 17 Hertz. Our constant value for the speed of light is 3 times 10 raised to 8 meter per second. And our required, we are looking for frequency. For our solution, we are going to use the formula F equals to speed of light divided by wavelength. We will substitute the value of C, which is 3 times 10 raised to 8 meter per second, divided by the value for wavelength, that is 4.80 times 10 raised to 17 Hertz. If we are going to divide these values, the value for F, which is our answer, will be 6.25 times 10 raised to negative 10 meters. Now let us sum up the concept you have learned in this module. A wave is a disturbance that transfers energy. James Clerk Maxwell formulated the electromagnetic wave theory, which says that an oscillating electric current should be capable of radiating energy in the form of electromagnetic waves. Henry Hertz discovered the Hertzian wave, which is now known as radio waves. Hertz is the unit used to measure the frequency of waves. Remember also that EM waves have unique properties. These properties are: EM waves can travel through a vacuum. EM waves travel at a speed which is constant in a given medium and has a value of C equals to 3.0 times 10 raised to 8 meter per second in vacuum. EM waves are disturbances in a field rather than in a medium. EM waves have an electric field that travels perpendicular with the magnetic field. And EM waves form when moving charged particles transfer energy through a field. Lastly, the wave speed, frequency, and wavelength are related by the following equation. V equals to lambda F, where V is equals to wave speed or the C, speed of light, expressed in meters per second. Lambda equals to wavelength expressed in meters, and F equals to frequency expressed in hertz. That ends our discussion for today, and I hope you learned something. See you in my next video for the next module. Have fun learning. Goodbye!